Hey everyone, and welcome to today's Explainer. I'm super excited about this one because we're going to demystify the foundational logic behind how software actually thinks. We're putting a magnifying glass on selection statements in the C programming language. So if you've ever wondered how a block of code knows exactly what to do next, well, you're in exactly the right place.
Okay, let's dive into this. At the very core of programming, we have a fundamental question. How do programs make decisions? How does code look at a situation, evaluate it, and know which path to take? It kind of feels like magic sometimes, but as you'll see, it really all boils down to very specific, beautifully structured logic.
By the end of this explainer, you're going to walk away with some serious programming superpowers. First, we'll make sure you can easily explain all the different variants of selection statements. Second, you'll know how to actually write a program using them. And third, you'll be able to look at any given problem and choose the absolute best, most efficient statement for the job. Here's our roadmap for today. We'll start with directing the flow, then look at the simple if statement, the if-else fork, nesting for deeper logic, the else-if ladder, and finally, the switch statement. First up, directing the flow, the basics of decision-making. So before we jump into the syntax, let's define what we're talking about. A selection statement is essentially a decision-making or control statement. On the basis of the application, we use these to test logical conditions and alter or control the flow of execution. Without them, your program would just run blindly from top to bottom. Think of these statements as the steering wheel for your code. Let's look at our first tool, the simple if statement, the one-way street. In C, the syntax is super straightforward. You literally just write if, put your condition in parentheses, and then put your executable statements inside curly braces. It mirrors how our own brains work. Our source gives a couple of great real-world analogies. If your bank balance is 0, you borrow money. Or if the room is dark, you put on the light. If the condition is true, you take the action. If it's false, you do nothing. Now, what's really interesting about this slide is the visual breakdown. See that diamond shape? That's our condition. If it evaluates to true, the flow travels to the right, executes the statement block, and then rejoins the main path. But look at the false path. It just goes straight down. It completely bypasses the statement block and moves right along. To put this into a concrete programming scenario from our source, imagine writing an application to check whether an entered number is less than 10. If the user types 5, the condition evaluates to true, and your program might print something like, number is less than 10. But if they type 15, the condition is false. The program skips the print statement entirely and just keeps going. Simple, right? But what if we need a backup plan when the condition is false? That brings us to the if-else fork, adding a backup plan. Looking at this flowchart, our condition diamond now splits the program into two completely distinct paths. If it's true, we execute statement 2. But if it's false, we don't just skip ahead anymore. Instead, we execute a dedicated backup plan, which is statement 3. You are forced to take one of these two roads before moving on to statement 4. The syntax for this is just a natural extension of what we already learned. We just add the word else and a new set of curly braces for the false outcome. The source highlights a great application for this. Say you want to add two numbers and check if their sum is in the range of 100 to 200. With an if-else statement, you can print one message if it's within that range, and a totally different message if it falls completely outside of it. Let's turn it up a notch. Next is nesting for deeper logic, decisions within decisions. Okay, let's trace this flowchart. We start with condition 1. If it's true, we don't just execute a final statement right away. Instead, that true path leads immediately into another diamond, condition 2. This lets us evaluate multiple, interconnected layers of criteria. It's the program's way of saying, all right, the first test passed, but let's check one more specific thing before we act. Nesting is absolutely perfect for bounding problems. Taking a scenario directly from the text, imagine checking if an input number is strictly within the range of 10 to 100. Your first if checks, is it greater than or equal to 10? If so, your nested if follows up with, okay, but is it also less than or equal to 100? It's a fantastic way to pinpoint exact scenarios. But what happens when simple nesting gets too cumbersome? We use the else-if ladder, multi-path decision-making. And this brilliantly illustrates the concept. Instead of going deeper horizontally into nested blocks, the logic cascades down vertically. It checks condition 1. If it's false, it drops down to condition 2. False again, down to condition 3. It's this very orderly, step-by-step chain of decisions, where the fallback for each else is simply another if check.
So the golden rule here is that control passes down to the next else block until a condition is actually satisfied. Once it hits a true condition, it executes that block and skips the rest of the ladder completely. The whole process continues downwards until there is no if attached to the very last else, which acts as your ultimate fallback.
Let's bring this abstract ladder back to reality. The source uses the example of calculating an electricity bill based on units consumed. If you use a small amount, you pay one rate. Else if you use a bit more, you pay a higher rate. And if you consume more than 200 units, you incur the top-tier rate, which the text notes as new 3.5. The else if ladder was literally built for this kind of tiered logic.
Finally, we have our last variant, the switch statement, the clean alternative.
When you have very specific multipath scenarios, switch is a real game changer. It evaluates a single expression and then searches for a matching case value. It's incredibly clean. You just write case value 1, case value 2, and so on. Notice the break statement, though, that's absolutely crucial. It tells the program to stop checking cases once it finds a match. And that default block at the end, that's your safety net for when nothing matches. Just like the final else in our ladder.
So, what does this all mean for you? The big question now is, which selection statement will you choose for your next project? Let's do a super quick recap of our complexity ladder. Use the simple if for a straightforward one-way decision. Go with if-else for a strict two-way fork when you definitely need a backup plan. Turn to nested ifs or the else-if ladder for those multipath chains and overlapping ranges. And reach for the switch statement when you want really clean, exact case matching.
To wrap up, I want to leave you with something to think about. Imagine you inherit a massive, incredibly messy, deeply nested if-else code block from another programmer. Knowing what you know now about these tools, how would you optimize it? How could you clean up that chaos into something elegant and readable? Keep that in the back of your mind the next time you sit down to write some code. Thanks for hanging out with me for this explainer, and I'll catch you next time.